So we were discussing about, we started discussing about noise. More specifically, we started discussing about thermal noise. And in the last class, we kind of introduced what are the genesis of thermal noise is with the example of a resistor. And this is what we saw, that if we have a resistor and let's say you tap out these two terminals, the resistor is floating and not connected anywhere, and I pass it and I interface this with a band pass filter of, let's say, a bandwidth of 1 hertz, and it is centered at some any arbitrary frequency if not. And we observe the power here, right? So let's say I have a power meter. By the way, when we say power, I essentially, even though the terminology is power, this is basically variance meter, I should say. Okay. And we observe the output. This output is always 4 kTr, right? This power that the variance that you are going to observe is always 4 kTr, regardless of the position of the F naught. Okay, so which essentially means that if I vary F naught, I check, let's say I check it at 1 megahertz, I get something. I take it at 10 megahertz, I get something, and I do it for all possible frequencies. And whatever we are getting, the variance will always be constant, and it's a flat line. And the value of this power per, this essentially boils down to variance per unit hertz, right? This is sigma squared by hertz, because we are observing over 1 hertz bandwidth. So this always comes out to be 4 kT times R. So couple of inherent assumptions that goes in this argument is the assumption is this 1 hertz bandwidth. This is kind of arbitrary because I chose 1 hertz because it makes the argument easier. But in principle, while I'm saying it's 1 hertz, the thing that I'm assuming is the path spectral density does not really change between let's say F naught minus half hertz to F naught plus half an hertz, right? That's the assumption that I am making. As it turns out, that's a way that for cases of these type of for thermal noise, that's a good enough assumption, or for most noise for that matter. But if you have to be strictly mathematical, then we should not limit ourselves to 1 hertz bandwidth. That should be like delta F, right? And delta F should tend to 0. And you ideally this should be delta F. And the power meter output, whatever you get, then you see sigma squared by delta F when delta F tends to 0, right? So this is essentially the definition of path spectral density, and we denote it as S. And if we are talking about the variance of voltage, we call this SV. Okay. Another thing that, but I mean, having said that, if you do for any practical purposes, if you do your experiment for 1 hertz bandwidth, you will not see any difference, because generally this thermal noise really hardly ever fluctuates, or for that matter, any noise. Okay, fine. Or rather, I should say it hardly ever changes abruptly between a frequency range of a hertz. Okay. The other thing that we should mention, I should mention is, yes. So now this time I didn't mention here, but I assume that we are doing voltage, right? So in the last class, I think I talked about current. Yeah. So, but I mean, you can talk about in current or voltage, doesn't matter. I mean, but 4 kTr, when you say 4 kTr, this is the observed path spectral density of the voltage, not the current. We'll talk about the current later. The other thing that I should explicitly mention, question? Other thing that I should explicitly mention is this 4 kTr is one-sided path spectral density. That is, when you're observing from 0 onwards, because you cannot physically observe negative frequency. right? You can only observe positive frequency. So if you do the experiment, you are always going to see 4 kTr. But for the mathematical purposes, right, when you do mathematics and you have to take into account negative frequency also in certain cases. For example, when you saw, when we decompose let's say a periodic sequence into Fourier series coefficients, you take into account negative frequencies also, right? Because maths is basically pushing you towards taking that into account, even though in principle negative frequency doesn't really exist. So, so, so when you, let's say you take a sinusoidal signal, right, and you express it in terms of Fourier series coefficient, one will be a positive frequency, other will be negative frequency, right? Equal j omega t plus e to the power minus j omega t. So one is at maybe at omega naught, another is at minus omega naught. And the power gets, or the amplitude gets distributed in this case, half here, half that side, right? So similarly, when you take any signal, which is, or rather in this case, noise, when you are distributing noise, when you are talking about noise, you are talking about essentially how much power you have within certain bandwidth, right? So now when you are talking about noise and you have to take into account for mathematical consequences, you have to take into account negative frequency also, then does it mean that we end up with 4 kTr in the negative side also? What do you think? What does your gut tell you? Is the question clear? Power has to. Correct. So essentially, the thing is the negative frequency is a mathematical construct. So whatever happens in the negative frequency, a mirror image should be there at the positive frequency. But what is the constant? The constant should be power, right? So if I observe the power between 1 Hz bandwidth here, right, and I do not take negative frequency into account, I should be able to get 4 kTr, right? So basically the area under this curve, correct? But if I take negative frequency into account mathematically and take both of them into account, then I should not be getting 8 kTr, right? Because that doesn't exist. But mathematically, it should come out to be same. So that's why when you take negative frequency into account, this can be sometimes mathematically tricky if you don't take care. So you have to assume that this is 2 kTr. So this is taking negative frequency account. Now, when you are doing LTI system analysis, this is not a problem if you take 4 kTr and do your analysis, because when you do an LTI system analysis, a signal, if a signal is applied at a certain frequency, the output will also be at same frequency. But if you are using a non-LTI system, then there can be frequency translation, right? And now readily you should be able to, even without doing math, you should be able to appreciate the fact that if there is frequency translation of signal, then there can be frequency translation of noise also, right? Because ultimately it exists in some frequency bin. And if your signal if you are splitting up your signal in Fourier series coefficients, which has a negative frequency component, then in order to do justice to how the noise is also getting affected, you have to take into account the negative frequency of the noise also, right? So we'll talk about this when we come to LPTV systems in more detail. We'll talk about these things, but the thing that you should sometimes can lead to mathematical discrepancy is if you do your analysis using 4 kTr or you do your analysis in 2 kTr, you might not get similar results. If you do not get, then you go back and check whether this assumption that you have taken is valid or not. If you take 2 kTr, you have to take both sides of the spectrum into account for doing all the analysis. If you take only 4 kTr, you have to take only one side, but you have to ensure that you are not taking the negative frequency for anything, not even for your signal, right? So be consistent in whatever you are doing and you'll be fine, right? So that is something that you keep in mind, keep the back of your mind. Till your midsem, you don't have to bother about this because we are not going into negative frequency translation of noise till then. But after that, you will start seeing these effects. Okay, fine. So now let's start moving into the analysis of noise, or rather, if noise is present in a network or a circuit, how should we go about dealing with it, right? Okay. So let's say I have resistor. And after that, I have a block which acts as an amplifier and gives a voltage gain of A. Right. So this is, by the way, A is a voltage gain I'm talking about here. Not power gain, not current gain, it's a voltage gain. And let's assume that the input impedance is infinite. Right. Okay. And I observe the output here, V naught. Right. So there is no signal anywhere. Right. There is no signal anywhere. So I should not get any signal out. Right. The signal should be 0. But will I get a noise? Will I get a noise output? I'll get noise output, right? And what can you comment on what will be the power spectral density of the noise that we'll observe? Right. So basically it will be A squared times 4 KTR, but why? How do you go about thinking about it? So in order to understand how do you go about thinking about it, so we have to understand that what we are saying is, if we just take a resistor and observe the power spectral density here, so I am getting some noise. In time domain, I'll get some noise, I'll get some fluctuation, which I model it as Vn. So this is a noisy resistor. Which gives a if you plug in a voltmeter at the terminals, you are going to get some voltage, even though there is no signal attached to it, even though nothing is attached to it, right? So now, for circuit analysis, these type of representations is not particularly useful. We would like to keep the resistor as an element which always gives us V equal to IR. And if there is anything associated with it, we would like to remove it and make it a separate element out of it. That helps in circuit analysis. Okay. So which means that, I would like to form a scenario where the resistor is noiseless. This is. But I should still have, if I observe the voltage across these two terminals, I should still observe the same voltage Vn as I am observing in the previous case, right? So this will help us in isolating, this will help us in our circuit analysis. So, but clearly if this is noiseless, then I have to add something to it, right? So what should I add? I will add a voltage source. And the voltage source should be such that the power spectral density of this voltage source should be same as the power spectral density that I observe across the resistor. Correct? Now I have a question for you, that the voltage source, I can have it in series or I can have it in parallel. Voltage density, current. Yeah, but what is the issue? In either of these left hand side and the right hand side cases, I am still observing Vn here. So why can't I use this one? The current across it is fixed. Current across what is fixed? Across the parallel through the resistor. Okay, so something is fixed, but yeah, but you're in the right track, but that's not the current across it is fixed. It's not the voltage is fixed, right? So other way of thinking about it is that what is the, if you assume that this is your 2-port or this is your single port, not 2-port. So what is the impedance, equivalent impedance looking in? What is the Thevenin impedance? 0, right? But actually what the Thevenin impedance should be? It should be equal to R, right? If this is R. So just because you are wanting to model noise, that doesn't mean your R should go off. Right? So your Thevenin impedance should remain Thevenin impedance equivalent, right? So hence the parallel one is not the right way to model, that series one is the right way to model. So wherever you have a resistor in a network and you want to analyze its impact, so you have to then basically put a equivalent noise source in series with R, right? And then connect. So you remodify your circuit and then you connect. Okay. Okay. So just for the sake of completion, So this SVN will be 4 kTr. Okay, fine. What about now I want to model everything as a noise current, right? Because ultimately currents and voltages are brothers of each other. So if I can model something as a voltage, I should be able to model something with respect to current also, right? One is Thevenin equivalent, other is Norton equivalent, right? So I can model this as also a Norton equivalent, which is some noise current and a resistor in parallel to it. Right? Again, the same argument holds why it's not series, because if it's series, then equivalent resistance is infinite, right? So that should not be the case. So I call this IN, this is R. What is the expression for this IN? VN by R, right? So what will be the noise spectral density of this current? Why? Okay, so now in order to appreciate that, let me take a step back. So let's see if I take a resistance here, noiseless resistance, and a voltage source which is modeling the noise, right? And let's say this has a gain of A. I'm coming back to wherever we started. So clearly, the voltage that I'm going to observe here, assuming this is infinite, right? Rin is infinite, let's say, no loading. Okay. So the voltage that I'm observing across this terminal is also Vn, correct? So the output that I'm going to get is Vn times A, correct? So if I observe now, do the same experiment as we did with respect to finding out the noise of a resistor. So what did we do? We basically pass this through a band pass filter of certain center frequency, 1 Hz bandwidth, and observe the variance, correct? So what is the variance that I'll observe? If the input to this band pass filter is Vn times A, Vn squared times A squared, right? So Vn squared is basically the variance of Vn is, so if I say variance of Vn is sigma Vn, which is sigma squared Vn, which is known to us, right? So but now I am not observing the voltage variance of the resistor. I am observing the variance after the resistor has been interfaced with the amplifier. Okay. So which means that the variance here will be A squared times sigma Vn squared, right? Okay. So now, I mean, forget about this A now. This is basically any scalar, right? Mathematically, there is any scalar. So if now let's go back to this quantity. So what will be the variance of this guy? It will be variance of Vn squared times the scalar. What is the scalar? 1 over R, right? So basically 1 over R squared. So this is the variance of Vn squared per unit hertz, per unit bandwidth, let's say I call it per hertz. So is essentially 4 kTr by R squared. So this becomes 4 kT over R, correct? So when you express your noise in terms of current, your thermal noise in terms of current, the power spectral density of the current is 4 kT over R. Right? So units also kind of matches, right? Because if one is current, another is voltage. So if the voltage one is proportional to the resistance, the current one is inversely proportional to the resistance. So that kind of also makes sense. Another terminology that you are going to that I'm going to use and you are going to also hear a lot of time is often this white noise is also this thermal noise is also called white noise, right? It's white because ultimately the spectrum has all frequency components, right? And hence the term white. So it's white thermal noise. It's also called white Gaussian noise. The Gaussian term comes because if you check the statistics of it, the amplitude of the noise that you are going to observe over like infinite number of experiments is also Gaussian, right? So hence the term Gaussian. But all of these are interchangeably used, white thermal noise, white Gaussian noise, thermal noise, whatever, right? So, but whenever I talk about this in any one of these terms, you should automatically relate that we're talking about these kind of scenarios. Okay. Any questions so far? Okay. So now we did, what did we do? We introduced thermal noise. We talked about how to model it in terms of voltage. We talked about how to model it in terms of noise, in terms of current. We also talked about how to analyze it if I interface it with a scalar quantity, right? Now let's say I have a scenario where I have the same scenario. Assume the input impedance is infinite and all. And now this has a spectrum. It's not a scalar that increases every frequency component by A. I have a spectrum of h of omega. I want to understand what is the power spectral density of the output. So can you now help me out? What will this be? So let's do the same experiment. So what experiment? What thought experiment? I put a band pass filter of 1 hertz bandwidth. What am I going to get at the output? And I'm observing the power, right? What am I going to get? What am I going to get at the input here? So in terms of voltages, actual voltages, I should get h j omega times V in j omega, correct? But this V in j omega does not have any meaning because this is noise, right? I do the experiment now. I'm going to, and I take a Fourier transform of that sequence. I'm going to get some value. I do it tomorrow. After 1 second, I'm going to get a different value, right? So this V in j omega does not have any meaning. What does have a meaning is the statistics, right? So I know the variance here. So I have sigma squared Vn will be the variance, right? But I'll have, so now I'll have to scale it up with something, right? When it was A, I was scaling it up with A squared. Now what will I scale this up by? Mod of h of j omega square, right? Parseval's, basically Parseval's, right? In Parseval's, how do you calculate power? You take that mod of that thing and square it, right? So essentially you get mod of h of j omega whole square, right? So output will also be, the power spectral density will be sigma Vn squared, sigma Vn squared over 1 hertz bandwidth times mod of h j omega whole square. More mathematically, this is written as SVN. Power spectral density is always per unit hertz. So SVN times mod of h of j omega square. Okay, fine. So that takes care of if I have a frequency dependent component anywhere, how to handle noise, right? So now let's do an example, and then probably it will make more sense. So let's. Yeah, so even though the units of power and variance are different, but we basically borrow the terminology from communication systems, where when we talk about power, we talk like x squared. We do not really multiply with r or divide by r. So if you have to marry these two concepts, assume that it is passed through a 1 ohm resistor, right? So then the power, whatever the power is, equivalent to that. But yeah, so that's an important distinction to make. Even though we are talking about power, the units are volt square per hertz or ampere square per hertz, right? It's not watt per hertz. Okay, so now let's take an example. So let's say I have a RC circuit. And it is being driven by some voltage source. Okay. This is not a noise voltage source. This is an actual voltage source. Let's say sine omega t or something. I want to find out what is the output noise. I am observing the voltage here. I want to find out what is the output noise. So how should I go about doing the analysis first? What is the first step? Of what to what? But V in is not noise source. V in is signal. Right. So first line of business is to find out whether there is a noise source. But there should be a noise source because I have a resistor, right? Which means even though I have not explicitly mentioned it, that is your job to understand that there is a noise source. And if noise analysis is asked for, then you have to replace the R with its noise equivalent model. And what is the noise equivalent model? Noiseless resistor with a voltage source in series. So basically, this is a noiseless resistor with a voltage source in series. Okay. So now I want to find out the noise. I want to find out that the noise power spectral density at the output. Now I see that I have two sources, right? I have this source and I have this source. When you have two sources, I want to find out the effect of one. What do you do? Yeah. So basically, if I know that V in is not a noise source. So if V in were a noise source, I would have done superposition of these two sources and then added up. But in this case, I have only one noise source, so I'll keep only that, right? I'll remove this. So this becomes as is. So now I know, what do I know? I know the power spectral density of the noise source, correct? And I'm interested in the power spectral density at the output. Okay. So now what should I do? I need to find out the transfer function from this noise source to output. Correct? So step 2 is find out the transfer function from the noise source to output. So let me write out the steps. The first step is replace all noisy elements with their noise equivalent model. Step 2 will be use superposition to find the output noise for each individual noise source. And step 3 will be combine. Correct? If here I have only one noise source, if we had like 2-3 different noise sources, then step 3 would have been to combine the effect of all. Now we'll talk about how to combine in shortly. Combine the effect of all. Okay, so this I have not mentioned how to combine. I'll come back to this. Okay, so but let's do the single noise source case first, then we'll talk about multiple. So now this is simple. So what is the transfer function from V0 to Vn? So h of j omega is V0 to Vn. For transfer function, you don't have to consider noise, right? You just assume that there is a voltage source there and you find out the transfer function. So wherever you have a voltage source for noise, you assume there is a explicit voltage source or a current source, however you are modeling the noise. And then you find out the transfer function from that point to the output. So in this case, what is the transfer function? This is simple. 1 + 1 by j omega RC, right? So what will be your power spectral density at V0? So S V0 will be SVN0, I should say, because I'm talking about noise, so I should always subscript it with N. So SVN0 will be power spectral density of Vn, which is 4 kTr divided by 1 plus omega square R square C square, right? Because I'm taking mod of that, right? Mod of 1 by j omega R C squared, right? Okay. Yes. Coming in?
SPN not.
Okay.
This is the noise factor.
Yeah. This is the noise pass factor density, correct? So if I have to, I skipped a step. So I basically have to say this is SVN times mod of H squared, which is 4 KTR by 1 plus omega square R squared C squared. So the question here.
Can use 2 KTR.
Yeah, so good question. So if I have to plot this, so how should I plot this? So this will become 4 KTR and then it will roll off, right? To asymptotically go to 0. So if this is 4 KTR, then this side I don't have anything because I have taken one side as spectral density. If I have to take two side as spectral density, then this should be 2 KTR and then this should go something like this. Right? So this is 2 KTR. Okay. So this is as far as doing a noise analysis in a simplistic resistor case is concerned. That now my question to you is, if I have to reduce noise, this question actually came up, I think Sarvesh asked this last time in a different context. If I have to reduce noise, what should I do? So this is 4 KTR. I know SVNO is 4 KTR by 1 plus omega square R square C square. So I want to reduce noise. What should I do? Let's say I'm interested in a very low frequency noise. So basically I'm interested here. Not like very high frequency, but low frequency noise. I can reduce the value of the resistance, right? So this is approximately equal to 4 KTR. So this is true for omega much lesser than the bandwidth, right? Less than 1 by RC. Right? I can reduce the R, but I mean, what best case is R equal to 0. Correct? I can do that. There is nothing that's stopping us from doing R equal to 0. Correct? So do you see an issue with that scenario? Right. So the thing is, we should not consider only about noise, because ultimately the whole purpose of designing a circuit is to process the signal. And noise is something that comes along with it. So we have to ensure that the noise does not play spoil sport. Correct. But you cannot unilaterally consider noise always. You have to consider the effect of both signal and noise. So essentially, we have to talk about signal to noise ratio. Right? We should not only consider noise. For example, even though this is not visible here, let's say I have a scenario where I have this no R, no C, for example. This is R, this is R, this is R1, this is R2. Voltage divider, simple voltage divider. Correct? So the simple way to kill noise is to short this. Correct? There is no noise, but there is no signal also. So this is useless, right? So you should not. So that's why you should not should not only consider noise. Sometimes it can be misleading that you might do a simple noise analysis, and it might appear that the noise is going down, but it might be at the expense of signal. Or sometimes it might appear that the noise is going up, but then you have to go back and check what this does to the signal transfer function. Is it also increasing the signal? So that ratio is important, right? So only considering only noise is not enough. So which means that we'll have to go back and find out what is the impact of the signal to noise ratio. So if I do that for this simple circuit, what should I see? So signal to noise ratio in this case is simple because the signal transfer function and the noise transfer function is identical. Correct? Because it's located, the signal position and the noise position is identical. Right? So noise is also here. Signal is also there. So in this case, your signal to noise ratio is 1. Correct? Or, okay, I should not say 1 because I assume that input signal also has the same power as the noise. That I shouldn't do. So let's say the signal has a signal is a sinusoid having amplitude Vp, right? So let's say Vp cosine omega naught t, right? So signal to noise ratio will be power of the signal by power of noise. Correct? Now you can express this power in multiple ways. One way to express that, I mean, one of the most common ways is to express it as power per hertz. Okay, so power per power for noise, especially power per unit bandwidth, right? So power of noise over 1 hertz. So essentially, the top becomes Vp squared over 2 times mod of h squared, correct? By 4 kTr times mod of h squared. So which essentially becomes Vp squared over 2 by 4 kTr for this particular circuit, right? Because mod of h will cancel for both cases because it's seeing the same transfer function, but did not necessarily be the case always, right? That's simple to assume that if you have resistor at somewhere else, the transfer function will not be the same. Okay. Okay, fine. So from here, what does it? So the goal will be, as a designer, the goal will be not to reduce noise, but to maximize signal to noise ratio. Correct? So what is this telling you? What is this expression telling you that what should I do to maximize signal to noise ratio? Increase the power of the input. That is something that we would like to do, right? So one of the reasons amplifiers are used is to increase the signal power before it is fed to a subsequent block, right? So if you know that one block is supposed to add some amount of noise, you ensure that its input has has as high a signal strength as possible, so that its own noise does not overwhelm the signal, right? So that is why one thing is clear is that in order to maximize SNR, or in order to mitigate the effect of noise, I should ensure that the signal is as high as possible, right? So that is point number one. If that is not in our control, let's say it is coming from somewhere else, the signal is coming from somewhere else. Let's say it is not in our control. If it is in our control, we are going to use it. We are going to use this handle. We have to maximize Vp. If it is not in our control, what can we do? Reduce noise power, right? In this case, the only thing that I can reduce is R, right? So that also, I mean, that makes sense. If I reduce R, then we kind of get maximize SNR, right? So within the bandwidth of interest. But I think he pointed out one important point. If I reduce R, right? So right now it seems like it's an easy fix. I reduce R, but if let's say I want to keep the bandwidth fixed, right? So reducing R and keeping the bandwidth fixed would mean, what should I do? I have to increase C. Correct? Makes sense, right? So I have to increase C. So if you cannot unilaterally go and reduce R if you have to keep the bandwidth fixed, right? So if you are making a filter, right? If you are making a filter, the assumption is that there is something happening out of band which you do not want. Otherwise, there's no point of making a filter. Why would you want to make a filter? So which means that you want to keep the bandwidth fixed. So if you are in a purpose quest to reduce noise or increase SNR, you should not be tampering with how the circuit is initially meant to behave. Correct? So which means that if in order to reduce, if you increase SNR by reducing R, you have to also take care of the capacitor. You have to increase. If you reduce R by a factor of 2, you increase R by increase capacitor also by a factor of 2. Okay. So that is something as a designer you should keep in mind. Now, but that is simple to do. I mean, that's not a problem. I can always do that. But is there a trade-off? Is there something I am paying with? Because everybody can do this. So what's the problem? I take a circuit, I reduce R, increase capacitor. Is there a penalty anywhere, or is it free lunch? Power dissipation. Where is the power dissipation? Area is a problem, I agree, because if you keep on increasing capacitor, on chip area will also take a hit. Well, let's say we are not bothered about area. Maybe you are doing discrete levels analysis, discrete circuits where the area does not scale with the value of the component as much. So in that case, is there a hit? Somebody said power, right? Why power? Where is the power? There is only R and a C. Can C consume power? No. Then what can consume power? R, right? So if you, so what can happen if you reduce R? Right? So effectively the current is going to increase and you are going to burn more power in the resistor. But where from will the power come from? The power is getting dissipated across R. Who is supplying the power? The source, right? The source naturally. So you are extracting more, you are demanding more power from the source. Correct. So that might or might not be possible all the time. Each source has some finite amount of power one can supply. So in this scenario, I have modeled the source as an ideal source with no resistance associated with it. But in principle, there will be some resistance. And if you draw more and more power, that is, you are drawing more and more current, you are going to see drop across that resistance. And hence, you will see all the voltage drops and across everything, right? So your circuit will not function as it was meant to be. If you simply add one resistance with the voltage source, you will see that as long as the resistance is much smaller than the R, then it's fine. But if in a quest of reducing noise, if you keep on reducing this R, then that assumption will not hold true. And hence you are going to see a lot of drop across the voltage source terminals itself. Right? So that's a downside. So if I formalize this with the so, so your voltage across this is V in by 1 plus j omega RC. So the current is always j omega C times this, correct? So I in is P in times j omega C by 1 plus j omega RC. So the power dissipated across the resistor is I in, so this will be VPP squared by 2, or VP squared by 2 times this omega square C square by 1 plus omega square R square C square times R, right? So this is power dissipation. Okay, fine. So an SNR is always VP squared by 2 times 4 KTR. Okay. So your power dissipation. So intuitively, what it appears to us is if I reduce R, I should be having more power dissipation, right? So that's, but that's not what we are observing here. There is some issue. So if I do power dissipation, P dis by SNR, or SNR by P dissipation. Okay. So Is this fine? Okay. Okay, so let's isolate the terms. Vp squared by this goes 4k times omega. Oh, now I understand what's the issue. I think I do. So omega squared c squared times r times 1 plus omega square r square c squared. So yes,
denominator both will cancel.
Vp and the denominator will cancel. That is correct. So this goes. So you're following the algebra, right? I'm not making any mistake so far. Okay, fine. So I don't trust myself. R square. Okay. Hmm.
Now we will assume.
No, there is some issue. I mean, something got cancelled which you shouldn't have, right? Vp square. This is fine. This is fine. I got Vp square. This got cancelled. R square is okay. Okay. Okay, so so let's go with this only. So we are what are we planning to keep at, if we want to increase if I want to increase the SNR while keeping, okay, now it kind of makes sense. So what we want to, the part that I mentioned, but I didn't tie up with the analysis, is the fact that we do not want to change the circuit configuration in the sense that we want to keep the bandwidth constant, correct? Which means that if we increase R, right, we'll have to decrease C and vice versa, right? We want to keep CR to be constant, correct? So which essentially means that this is not a free variable, correct? So RC is constant. We are keeping RC to be constant, correct? So what if this is constant, then you see this ratio of SNR by P dissipation is constant, right? Does that make sense? So if bandwidth, so if 3 dB or omega 3 dB is same, then RC is constant, correct? So which essentially means that your SNR by P dissipation, power dissipation is constant. Right? Which means that, naturally means that if you have to buy SNR, you'll have to pay with power, right? So the SNR is proportional to power dissipation, right? Does this make sense or did I confuse you even more? I think I confuse people. Okay, so let's unpack. So you are okay with this expression? Okay, you're okay with this expression? Okay, so all I did was to take a ratio of SNR and power dissipation, these two expressions. Okay, and I ended up with this. Fine. So now I am staring at this equation and trying to figure out, I have got some signal to noise ratio, right? So let's say I got 10 dB signal to noise ratio. Ratio I can always express in dB. I want to increase the signal to noise ratio by another 3 dB. I have to double it, right? So what handle do I have? So and the assumption is that I do not want to change my circuit. I do not want to change the transfer function of the circuit. When I say circuit, I mean transfer function of the circuit. Correct? So which essentially means that it is pointing to you that if you reduce R, that we saw, right? If I reduce R, I can increase SNR, but then I have to increase capacitor. But what impact does it have on power dissipation? It also doubles, because this is what This is what this relationship becomes sacrosanct. Right? Your SNR, the ratio of SNR to participation for a particular circuit, for a particular configuration of a circuit is always constant. I mean, I took the example of one specific case, right? But in general, also we can show that this ratio is always constant. All you have to do, so I shouldn't say all you have to do. So what this is telling you that if you have a particular network configuration, in this case that RC network, the only way you can increase SNR is by paying with power. You want to double SNR, you have to double power. Right? So doubling power in this case, I mean, doubling SNR in this case meant that you reduce R by factor of 2. Right? Which means that you are intuitively also you should be able to figure that then you are doubling the amount of power that you are drawing from the source. That you are drawing more current. Right? You are for the same voltage, you are drawing double the current, which means that you are spending double the power. So increasing SNR and increasing power dissipation go hand in hand. That's what this particular network, this particular expression is telling you for this particular network. But I can also generalize it. So the way I will generalize it is as follows. So let's say I have a network and I have multiple resistors inside, resistors, capacitors, and so on. And each of these resistors are noisy. Fine. So I am interested in finding out, let's say there is an input somewhere, I found out the SNR. Okay. I found out the noise signal transfer function. So I'll add, let's say I have an input here. This is V in, this is V naught. Okay. So let's say I take another network. I take another identical network. This is N. I take another identical network, N. This is capacitor and everything is there. And I connect these two networks node to node. What I mean in parallel, what I mean is this node connects here, this node connects here. This node connects here, this node connects here. Similarly, internally also, if I have a node here, this connects here, this one connects there, and so on, right? Looks ugly, but you kind of get the idea that I take two circuits and connect these two node to node, without missing any node. So I'm basically putting two circuits in parallel. So can you comment on the current that will flow through each of these wires? No, through these connecting wires between these two networks. It will be 0, right? Because two circuits which are connected node to node, which means they are behaving identically as far as the signal transfer function is concerned. So if there are two nodes which have same potential, there cannot be any current through the connecting wire. Right? Make sense? Okay. So which essentially means that even if I connect two things parallelly, node to node, your V0 over V in does not change. Correct? Your signal transfer function does not change. Make sense? All we have to establish is what happens to the noise. Because each of these two circuits have noisy resistors inside. I establish the signal transfer function does not change. If I can establish that the noise changes, then I can have a argument that what should we do in order to change SNR. Correct? Can you also comment on the power? If I connect these two networks like the way I showed, can you comment on the power dissipated in the network with respect to the previous case when we had only one network? Twice, right? If one network has PDIS, two networks will have twice PDIS, right? So we have established two things. The power, if we connect it like this, the power dissipation doubles and the signal transfer function doesn't change. Right? Now we have to establish what happens to the noise. Okay, that's what we are going to do next. So let's see that. So for noise, I do not need to bother about the input. right? So input gets shorted. And I am showing only one representative resistor inside. So you can have multiple of these resistors. Okay. So I am interested in finding out what is the impact of noise at the output. I probably have missed one step because before I go there, I have to join some dots. So one dot is this. So let's say I have so I'm taking a step back. I forgot to talk about this. So let's say I have a network. I have two resistors here. They are not necessarily connected in any particular manner, but it's part of a network. Okay. So each of these resistors has a noise. I can model them as a noise source in series with them. This is R1, this is R2. This is Vn1, this is Vn2. And the transfer function from Vn1 and Vn2 are known to us. Let's say this transfer function from this to V and this to this are known. So let's say this transfer function is H1 and this transfer function is H2. Okay. So I need to find out what is the impact of noise when I consider both of these two noises simultaneously. So what I essentially mean is if I have two of these noise sources working in unison, how do I use superposition? That's the question. Okay. So I understand that there will be, if I use Vn1, I'm going to get an output which is H1 mod of H1 squared times 4 KTR1. Right. So this is for R1, noise due to R1. Noise due to R2 will be H2 squared times 4 KT R2. This is for R2. Correct? Okay. So now my question is, if I combine both of them together in a network, what will be the combined noise? Yeah. So for that, in order to establish that, I would like to point out the following. So let's say you have a network which has two voltage sources of different frequencies. Okay. So let's say I have a network having two voltage. Let's say this is V in 1 and this is V in 2 operating at omega 1, operating at omega 2, where omega 1 is not equal to omega 2. Okay. And I want to find out the power at the output. Okay. So what can I essentially say? I can be, if I do the voltage analysis first, your output will be something like Vp1 cosine omega 1t times some h1, correct? If I say h1 is a scalar, then it doesn't really matter. If you have a vector, then you have another term, plus Vp2 cosine omega naught omega 2t times h2, correct? And if I have to do the power of this combined signal, then what do? I take I square it and take an average of that. Correct? So if I square it and take an average, what do you end up with? You end up with three terms. One term is Vp1 mod of h1 squared cosine squared omega 1t. Another is Vp2 squared mod of h2 squared cosine squared omega 2t. Another term is a cross product term, which is Vp1, Vp2, twice of that. H1, H2, cosine omega 1t, cosine omega 2t. And you take the average, right, of all three. So can you comment on the average of this guy, last term? 0, right? But the average of the first two terms are not 0. That's why, I mean, you get twice omega 1 term or twice omega 2 term, that goes to 0, but you get another DC term, that is Vp1 squared H1 squared by 2 and Vp2 squared H2 squared by 2. They contribute to the power. I mean, they are the power terms, right? So this will be Vp1 squared mod H1 squared by 2. And this is VP2 squared mod H2 squared by 2. So they are the power term. Everything else goes to 0 when you take the average, right? So key thing to note here is that when you are considering power for different frequencies, then it's like superposition of the power terms for each individual cases, right? So I can basically say that I can find out the power for this network with one signal attached at a time. I can do one with this while this shorted, and I will only get this term. I find out the power corresponding to that. Then I do with this shorted. Then I'm going to get the power corresponding to this. So whatever power I get, I square, add. Right? So when you have different frequencies at play, superposition is allowed for power. Right? You do not have to bother about phases. That's why the superposition is allowed for power when different frequencies are at play. Now, similarly, when you are doing noise, noise has like all frequency components. And if the strength of the noise at any particular frequency is 0, because power spectral density is power within one delta f bandwidth while delta f tends to 0. If delta f is actually 0, right, which is at particular frequency, then the noise component at that particular frequency is always 0. Right? So essentially, when you have multiple noise sources in play, it is equivalent to saying there are multiple noise sources at different frequencies at play. Right? Doesn't make sense? So I'll talk about in a way that probably makes sense. So let me finish this thought. So the key thing that I'm pointing out here is that when you have multiple noise sources at play, all you have to do is find out the power spectral density for each of these individual cases and add them up. You don't have to bother about the cross terms. So if you are comfortable with correlation, then it is equivalent to saying that the cross correlation of the noise sources is equal to 0. That's because each noise source is uncorrelated with its neighboring noise source. Right? So there is no correlation between one noise from one resistor with respect to the noise coming from another resistor. Right? So when you multiply the effects and do an average, which effectively means that the average will go to 0. Right? So it is, so what I'm saying is if you have one noise source which gives you Vn1 square, another noise source which gives you Vn2 square, the cross term will lead Vn1 times Vn2 average. This will always go to 0. Okay. And you will end up with sigma Vn1 squared plus sigma Vn2 squared. Okay. So which essentially means that when you have multiple of these noise sources together, we're almost out of time. When we have multiple of these noise sources together, all you have to do is find out the output noise for each individual cases and add them up in power. Right? So which essentially means if I know the transfer function from here and here to output, and I know this is H1, I know this is H2. So the total noise at the output will be 4, this is R1, this is R2, 4 KT R1 times mod of H1 squared plus 4 KT R2 times mod of H2 squared. Right? So as far as circuit analysis is concerned, this is all we need to do. The theory behind it is whatever I said 2 minutes back. Okay. Make sense? Okay. So now this is, if I have like K of these resistances, I have N of these resistances, I can basically say that noise power spectral density is VNO will be 4 KT summation over RK mod of HK squared over all K. Right? Okay. Now, what did we do? The experiment that we did was we had this identical, we made a copy of this and connected them node to node. Right? This is what we did. So now can you comment what can I replace this is the total output noise with this expression with when I combine these two circuits together? what is the easiest thing that I can do? Will HK change? HK will not change, right? Will RK change?
Yes.
And what will happen to RK? It will go to by 2, right? It essentially goes by 2, right? So if a RK goes by 2, what can you comment on the total noise output? Output noise also goes down by a factor of 2, right? So what did we now if we tie everything together, if I have these two networks which are tied in parallel node to node, his output voltage power spectral density goes down by a factor of 2. His signal power does not change, right? Which means SNR goes up by a factor of 2, but at the cost of power, because power also has gone up by a factor of 2. Correct? So fundamentally, even without taking a specific example, you should be able to appreciate that in order to increase your signal to noise ratio by a factor of 2, you have to burn double the amount of power. This is fundamental to, this is for thermal noise, this is fundamental for any circuit. Okay. Or rather for, I should say, for any LTI circuit so far, right? This is only LTI. We have not really considered noise folding from multiple frequencies. So now if somebody tells you that I have a circuit which is like gives excellent noise performance, like extremely low noise, the first thing that you need to ask is that, okay, tell me, I understand how much power have you burned? Right? Because I have a network, I have a circuit which gives you, let's say, so much of power spectral density, let's say, I don't know, maybe 10 nanovolt per square root hertz. I just picked up a number. And somebody tells you I have like 5 nanovolt per square root hertz, or like when I say square root hertz, I mean I took a square root of the power case, right? So then naturally the curiosity should be that how much power the other person is burning in order to reduce the noise. If I am burning twice the amount of power to get twice the SNR, then big deal, I can also do that. Right? I can just take my circuit, copy it, connect node to node, done. Don't have to do anything. Right? You get extra SNR. Right? But so that's why SNR and power go hand in hand. Quoting one without quoting the other does not make any sense. Okay? Okay, fine. We'll stop here.